Good morning. My name is Eider Robles. I work in Tecnalia in the offshore renewable energy platform. And today I'm going to talk about the use case 2, where we have worked on the electrical generator of an WEC. Three partners take part in this user case, Tecnalia, IDOM, and WEC. We want to analyze the failure mode of the electrical generator. We are going to use for that the technology of the oscillating water column. This technology has been demonstrated for a long time at the Mutriku Shoreline OWC plant since 2011, but also the floating OWC of IDOM was tested during 2.5 years in the WEC OpenSea testing site within the Opera project. What we are going to do is to try to demonstrate and to generate this degradation or this failure in the Tecnalia test bench. As we see here, the electrical generator is in the critical path of the energy conversion, and following the major issues experienced in the past, and also in accordance with the opinions of other developers in this field, the PTO subsystem is the most critical component of the technology. Why is this? Well, because we have to include a generator that can absorb peaks in high peaks, several times the mean power, and this contributes also to the yearly power generation because we don't want to penalize the overall efficiency too much during low power waves that occur most of the time. We know that the stator winding is responsible for the 65% of all the failures within the generator. We know that the main stress factors are thermal, electrical degradation, and also external environment. This last one, the external environment, also plays a role, but it's difficult to reproduce in a lab without specialized equipment such as climatic chamber, so it was skipped in the project. But the two important outputs from the work that in this project have been the generator sizing, because a big amount of time the generator works very far below its rate. But also a great part of the time it will need to withstand high power peaks. So it's a trade, this sizing. And on the other hand, also to find a condition monitoring technique for preventive control method in order to increase the reliability and try to decrease the OPEX. And how have we worked on that? Well, this is our hybrid testing setup. On the one hand, we have the digital models. We need a model of the device, OWC model. We have used also an efficiency model that taking the torques and inputs from the OWC model, it's able to give us the losses. We have also a thermal model that taking these losses is going to give us the estimated temperature, and we also have a degradation model that based on this temperature is going to give us the degradation of the estimation of the remaining useful life. And also we are going to use the experimental models. In this case, we have a test bench in Tecnalia where we have developed all the duration accelerated tests. It is completely sensorized because we need to try, we have been trying different condition monitoring techniques, and so we need a lot of sensors and measurements. And also we have data sets from the time the MARMOC device was installed in real in the sea by WEC. So we have a lot of information about the real behavior of the device in the sea. And what else? We have also the Mutriku power plant where we also have a fixed OWC. We are going to see later that we have been doing some tests, and the lessons learned in the project have been applied to the Mutriku power plant during the project. This is just a schematic of the test bench we have in Tecnalia, where we have a part which is emulated, the connection to the grid, the power converter, and the induction motor, the drive motor, that represents the behavior of the wave energy converter. And then we have an emulated real part where we have the real generator we want to test, and the power converter to connect it to the grid, and all the sensors we want to use for the condition monitoring techniques. And just a picture of the real test bench, where this is the power converter that drives the induction motor, the drive motor. Here we have the torque meter. We have the electrical generator under test, all the sensors we need for the condition monitoring. And this here is the back-to-back converter that it's going to convert the electrical generator to connect it to the grid. And say that this power converter and this electrical generator are the real ones that will be in the OWVC. Now we are going to go through the digital models we have used in the user case. As I was saying, the OWC model, the efficiency model, thermal model, and the degradation model. Starting with the efficiency model, just to say that the tests we have performed have been some at constant torque and some at variable torque to try to represent the peaks that the generator will withstand in the sea. Just say that the tests have been performed at constant speed for easiness of the testing procedure. Well, if we go to the efficiency model, here we see that the efficiency depends in the capacity factor. In blue, we can see the test we have performed with no peaks. And then the orange, gray, and yellow lines represent the tests that have been performed with peaks, from lower peaks to higher peaks. So it's easy to see first that the best efficiency is achieved around the 80% of the capacity factor. The generator is withstanding quite well the high over torques as well. Here you see that we have done tests up to 1.6. In reality, we have gone further in the torque, but it's not represented here. And we see that efficiency goes down when on the peaks in the input are higher. So if we have the generator working with high peaks, the efficiency is going to be a bit lower. What else have we done? With the efficiency model, we have been able to take this information from the test and to represent and obtain the segregation of the generator losses. Here we can see that the biggest losses are the copper losses in the stator. It's a quite difference with the rest of the losses, and also that these losses are still higher when we go higher in the capacity factor. So the percentage of the losses goes increasing when we increase the capacity factor. So the generator is working at higher overloads. And remember that these losses, the copper losses, are the ones that are generating temperature. So more losses, more temperature. Regarding the thermal model, I'm not going through into the details, but just to say that we have different variations of the thermal model. But as you see here in this site, this is a comparison between the response of one of the thermal models we have developed and the temperature of the stator winding of the generator installed in Mutrigo. So more or less, we are able to achieve the temperature of the chamber. Moving now to the degradation model, we have worked on the Arrhenius degradation model. Just to say here that the insulation of the generators we have used is a class F with a maximum temperature of 155 degrees and an estimated life of 20,000 hours. Under operation at that temperature. But the reality is that we are not going to be working at this temperature. We are going to have the generator working at higher temperatures. So the evolution of the remaining useful life of the different classes versus the temperature is what you can see in this graph here. On the different maximum allowable temperatures by design of the classes in the left side. So we have modified a model of an Arrhenius model to be able to estimate when the generator is going to break and which is the useful life depending on the temperature. Now I'm going to talk about the different condition monitoring techniques or alternatives in order to understand the behavior of the generator under this special regime to see if we can somehow estimate the degradation of the insulation of the winding in order to detect that it's going to break, but before it breaks. So the reality has shown us that it's not so easy, it's not so straightforward to detect or to estimate the evolution of this degradation. We're able to detect the breakage, but we are not really able to analyze this evolution because the degradation is not linear. These are the condition monitoring techniques we have applied on the test bench. So we have partial discharge, electrical signature analysis, park vector approach, extended park vector approach, and the most simple one, that is estimation of the temperature and degradation model. If we start with the partial discharge, say that the partial discharge are localized breakdowns or flashovers in a small portion of the insulation. Using sensors to detect this discharge within the installation is a really common approach in this condition monitoring. They are indicative of the insulation degradation. So we can use advanced monitoring systems like the ones we have here, the capacitors and current sensors, to analyze the frequency, the magnitude, and the location of this partial discharge. This provides information of the condition of the insulation. The reality is that in our case, it has not been possible to detect this condition because we have a lot of noise in the test bench. So this information is not possible to obtain for partial discharge. This is the reality because of the high noise. If we move to the electrical signature analysis, we have the motor current signature analysis and also the voltage signature analysis. This is a methodology that involves analyzing the electrical current or voltage signature of the electrical motors or generators to detect and to diagnose faults or some abnormalities in the system. It relies on the principle that the current waveform of an electrical motor generator has information about the condition and its performance. So we have to find the frequencies that are going to detect the different failures, and if these frequencies can be found in the current, for example, this implies that this failure is being produced. So here we see the frequencies that are implied in the MCSA and the VCSA, and the ones that we have found related to the generator winding insulation failure. Some of them have been detected, but the reality is that the results are not consistent enough. The peaks we have detected here are not big enough, so we are able to detect when the generator is broken, but we cannot estimate the degradation with information sufficient to say that we are finding the evolution of this degradation. Now we move to the next one, to the Parks vector approach. In this case, what we do is to convert the current to Park signals, ED and IQ. And if there is no any abnormality, so if the currents are well balanced in normal conditions, we see a perfect cycle. But when there are some abnormalities, so it detects there are some problems, they are not balanced, and we see different forms, let's say. And again, we have analyzed this approach from the initial condition where we see that there is no imbalance, and we have seen that over the different tests we have performed, this form has been changing until the complete breakage of the generator. And yes, this gives us enough information to say that something is happening, but we cannot measure the level of degradation with this technique. Next, we have the extended parks vector approach that builds upon the traditional parks vector approach. In this case, we have a new advanced signal processing algorithms and computational methods. Here the results, yes, they really present a direct correlation between the amplitude of this spectral component and the level of symmetry present in the motor winding, but it has not been appreciated a clear increment of the frequency during the monitorization of the test. So it's not useful, or at least we have not seen it useful to predict when the future failure is going to happen. So it only detects when it has already happened. This is again the same thing that in the previous cases. Finally, we have been recording the temperature during all the tests. Here we see the representation of the final stator winding insulation temperature over the different tests. We see that the exposure time in hours versus the stator winding temperature in Celsius degrees, taking into account that the tests have been carried out with a constant and variable mechanical input power. So in green, we can see the test and the temperature of the test in constant mechanical input power, and in blue, the tests that have been carried out with variable input power. So here, what we have done is to analyze the collection of tests that have reached a temperature above 135 degrees, despite the thermal limit is 155 degrees. So the blue line represents the instantaneous temperature during the test. The red solid line corresponds to the remaining useful life, the rule according to the theoretical degradation model. This model is based on the temperature exposure periods for class F insulation. But we have needed to do an adjustment in the degradation model to match the end of the life of the generator to the reality, from the theory to the reality. So the red dashed line is the remaining useful life obtained from the adjusted degradation model. We think that the reason for this adjustment is probably the cyclic loads that can accelerate the aging process of the insulation, because the theory only talks about the constant temperature, but it does not talk about the cyclic changes of temperature in the insulation. So probably this is the only method, only condition monitoring method that gives us a real evolution of the degradation. So what we think is that if we are able to estimate the temperature, these are measurements, but if we are able to estimate the temperature, this temperature can be input to the degradation model, and this degradation model is able to give us the remaining useful life, and it can be quite accurate, as we can see in this figure here. So this would be the best condition monitoring method from the ones we have tested. This has just some pictures of the barn starter winding. Once it was detected that it was broken, we opened the generator, and this is what we got, that starter winding was completely burned. And just the main conclusions of the user case is that the electrical generator starter winding failure is critical. We have performed accelerated iteration tests over 2 electrical generators to analyze different monitoring techniques. Some techniques have detected the starter winding failure, but at the end of the life of the electrical generator, but they have not detected the evolution of the insulation degradation. Here you have a table with the information of the different techniques analyzed, and the only one that we think that can be useful for estimating this degradation is the measurement of, or the estimation of the temperature combined with a good degradation model that gives us the remaining useful life based on this temperature. Well, that's all from my side. Thanks for your attention. This is my email, so I will be glad to answer any question you may have. You can post me an email and I will answer you. Bye.